Hello everyone. Let's look at digital signatures. We'll look at creating a key pair and we'll actually use the key pair. Then we'll verify it as well. So without further ado, let's begin. Okay, so this is my project. I've got cargo.toml with, let me just show you that. We've got SHA-2, RAND, hex, and ed25519 dash Dalek. And we've added rand underscore core as the features. Right, so if we change to source directory and we'll create main. I did have the one with the hello world, but I deleted it. Okay, so we want to use the ed type it from scratch 19 underscore Dalek. Just put in FM main so that it's happy with. And here, let's go for, we'll just add in, do we want sign in key, which can also be called secret key or private key. But because we're actually dealing with the elliptic curve signatures here, we're actually calling it the signing key because that's effectively what it is. But you will also, depending on the context, you will also hear secret key or private key. Signer. We also want verifier, which oftentimes you'll hear it called the verifying key. You'll hear called the public key. So quite a lot to import, but go right. And in addition to that, we will use. In fact, I don't know if I needed hex. Probably didn't. Let's just use. So we'll use rand rngs and then os rng, and that's going to use the operating systems. That looks okay to me. If I add allow unused up here, and then we'll recompile it. Good, that's clean. Right, so we've got the elliptic curve thing, which will generate the. We're going to generate a random number, which will generate. We'll use that to generate our signing key, and basically the signing key contains effectively the private key and the public key. So first thing we want to do is actually create the what's it called? It's the operating system's entropy source called cryptographically secure pseudo-random number generator. So we'll call it that just to be official. We'll call it CSPRNG, called OSRNG. And then we would do the signing key. This is a variable, so it's all lowercase in Rust. And that will actually be the signing key, the capital. Generate, is it going to offer me that? CSPRNG. And it will take the randomly generated number, and then from that it will bounce it around the elliptic curve, and we will end up with the signing key. Once you've got the signing key, you can generate your public key or extract your public key. Here we use verifying underscore key. So far so good. still compiles. And that's our key pair setup. So next, we're going to come up with a payload of some description. Because what we want to be doing is we want to sign a payload and then we want to verify it at the end. We'll verify it using the public key. This is important, the B, the lowercase b for bytes. In my example I did earlier, I had a comma there as well. I'll just make it exactly the same because I want to recognize that it's produced the same output. So we've got a payload, and then from the payload we can create a signature. So there's always three things. You have the public key, the private key, the signature. So using the signing key on the payload, get a signature. Let's signature, that's lowercase. We don't want the one that is offering us. That's Rust Analyzer offering the autocomplete that we don't want. Signing key, which is what we do want because that's what we created up on line, this line here. We want to use that signing key, and then we want to do dot sign, and then we'll put a payload in there. We'll run that does it, but obviously we're not displaying anything. Let's do an assert. So we'll do no, let's do that later. Right. I'll actually create a function to do that in due course. So let's what should we do? Let's just output the results. So we'll do like public key bytes equal, and then we'll just do public key to bytes. Seems happy. I don't know if we can print this yet. Let's try. Yeah, looks like it. There we go. That's our public key. So all of these numbers are between 0 and 256. And that number will be different each time we run it. So we got the public key. Let's just do the let's call it so we want the bytes of the signature. We'll just view that as well. That's signature underscore bytes equal signature 2 bytes. And then we are in a position where we can start printing and viewing what we've got. First, we'll display the public key. Bytes. And we don't need to do we don't need to use B in here. We've already converted it to bytes. So do public key bytes. Yep, it's good. So then we can do the hex encoding of it. So if I just copy that line, we'll call it public key hex. And here we just need to do I'm just going to use hex encode. It's not the only way, but it'll work. And it's fairly obvious what it's doing here. So we see, so we've got the original bytes, public key in bytes, and this is same under the bonnet. It's the same thing, but we're just displaying it as bytes. So 4f is 4 times 16. Sorry, 4 times, where is it? Up there, yeah, 79. The 4f 79, EE 238, and so on. See there, we've even got a 0. That one there. Right. So we've done the public key as bytes and as hex. We'll just do the signature now as well. So signature, sorry, and then we'll do bytes. And then we'll do that as hex as well. I did CI parentheses and it went to the outer one. Hex. And then we want to do that. We want to hex encode that as well. You don't need to you don't need to do all this hex encoding if you're working with it within functions. It's only to display the output you really want to need to do the hex encode. So now we've got the public key and we've got the signature. See signature down here. Signature is bytes, and we've got the signature as hex. See the 07 there is 7, 61 in hex is 97, so that's pretty good. Next, what we could do is we could just do the a little do a check author function, because typically that might be what we're actually using this for. To check auth. And we'll pass in a public key. We'll call it, that's the name of our variable, and that will actually be it'll be a, we'll borrow, or it'll be a reference to the verifying key. And then we want to pass in the payload, or we want to have a payload passed in, which will be, it'll be an array of U8s. So we pass in public key, payload, and we want to pass in signature as well. So signature and signature. These are all just that's the type. That's why it's got the capital. And then we just do bulk, so it's either true or false. So if the font's too big, so for the videos, I know some people watch on their phones. And fair enough, but just sometimes, especially with certain things, just I mean, how wide? I think there's 120 characters, and it just goes off the edge, doesn't it? So we want to take the public key, and then with the public key, we do verify, pass in the payload, and the signature. Then we need to do OK, because we want to actually return true, ideally. And I don't want that because I'm returning it. Okay, let's run that. Oh, it's not going to run because I've not used it. So we'll put an assert up here somewhere. The verification using checkauth function. Then we just do an assert. Checkauth. we, in fact, this just needs to be, we just do pass in the public key, payload, and signature. That need to be, we borrowed up. Don't need, it's a string slice, so borrow it anyway. I don't don't need to borrow that, do I? Because it's a string slice. It's not stored on the heap. What have we got in errors? Expected reference 29. Let's find reference. 120. Excuse the typing. So didn't like that. There we go. Sorry about that. That was just that was me getting in a muddle with the payload. So the payload, because it's a string slice, it didn't need to have the ampersand. Good. Right. That is how to use. Take that to there now. Format it. It's a bit nicer. This file is not including any crates, so Rust can't offer ID. So, oh, I think that might be because I deleted my main at the start before I'd started this video. I don't know. It's working anyway. So what we did was we created a random number generator. We passed in the random number that we generated into our generator to create a signing key, which is actually a pair, which is your public and your private key. We got the public key from signing key. So I put some notes down here, and no, I didn't. In fact, let me just read them out to you. So I typed some notes earlier. So it's to do with the length. So the length of the signing key is 64 bytes. The length of the public key is 32 bytes. So the signing key is 64. Signing key is basically the secret key and the public key. Or once you've got the secret key, you can derive the public key. So you'll often see, so public key typically is 32 bytes, but just watch out for a secret key because a secret key is technically 32 bytes, but the actual signing key is 64 because it's actually secret and the public, if that makes sense. But the signing contains secret and the public. That's how I understand it. If anyone wants to correct me on that, any comments are welcome. As I say, this channel's called Learning Rust. Actually, recently I've been looking at other frameworks without getting into too much detail. I've been looking at some smart contracts, which are a subset of Rust. But interestingly, they actually have their own types as well. So yeah, it's mainly for size and also to keep everything off the heap. So there's things like bytes n and symbols and things which I forget what it's called. I think it's called linear memory. So when you create a string, it doesn't get put onto the heap. It's not effectively. It's not really the stack either. It's called the linear memory. Lots of things to learn there. And what else? Yeah, I've just been mainly looking at signatures recently, and there's so much that depends on them. If you want to read about quantum computing and if it's going to crack all these, To my knowledge, it says that RSA and DSA are more likely to be, but EC, sorry, yeah, elliptic curve ECDSA is much less likely to be cracked by quantum computing. I think a lot of people are worrying about that now, and I don't think it's going to be a sudden thing. It will be gradual, and I don't know. Maybe someone will just get one working perfectly overnight. But like a lot of these things, I think it takes it's evolution rather than revolution. And I would imagine most of the banks will want to implement some new some new version of it. Won't even be SHA-256. You'll start to notice people using SHA-512 everywhere, where SHA-256 used to be used. But I would expect we might get a decent amount of warning. Who knows? Yeah, thanks for watching. Leave any comments, subscribe, thumbs up, and all the usual YouTube stuff. The algorithm, the famous YouTube algorithm, is a monster. And if you don't get views within the first 48 hours, you tend to just fade into obscurity. So yeah, for the first 2 days, if you're watching this within the first 2 days, comment, subscribe, thumbs up, and all that. Otherwise, this video will be gone forever. Thanks for watching, and I'll catch you soon.